All right, I'll be right back. All right, we'll go ahead and get started. Hang on just one sec here. I don't know why, but the Google Captions are not working. Try that again. Hello, hello. There we go. Cool. I don't know why they weren't working. Technology, that's why. All righty. So I did not get a chance to grade your exams yet. We did some family stuff and it took way longer than we anticipated. So I'll hopefully get them done by Wednesday, if not for sure, within the next few days. And I'm just checking to see who all has joined us on Zoom. All righty. So today we're gonna keep talking about how to lie with statistics, and we may get to our next lecture, which is how to lie with tables and charts. So this is the point in the semester where I just sort of play things by ear, see how things are going, and go from there. So the other reminder is if you haven't yet, make sure you turn in your bias in sources. I finally sorted them out of my mind, which is the activity we did in class last week where you found 2 more sources for your poster. and talked about potential sources of bias in them. So make sure that you get that in as well. And so today we're thinking about data analysis. And so that's not something we teach you how to do in this particular class. If you are interested in learning how to analyze data, you can take stats and research methods in our department, or the math department has a statistics course as well. And those are really good skills to have. So I do recommend that. But one of the things we want you to think about after this class is like, how are people analyzing their data? And data analysis itself is theorizing. When you go to run data analysis, they should be based off your hypotheses, right? This is what I hypothesize. Here is the test I can use to actually test that. And as you complete the data analyses, you should be thinking, weighing things, pondering, etc. So data analysis is thinking. So why do we need to think carefully about data analysis? And again, the Zoom folks, you can type stuff in the chat. Folks in person, feel free to just chime in. Why do we need to be careful and thoughtful when we're analyzing our data? Yeah, Mia. Your data. Yes, thank you, and sorry that I called you Nia. I don't know. I'm very tired after this weekend. It was a great weekend, but I like to feel focused, so bear with me today. Yeah.
Just to ensure that you're not kind of making a mistake with me.
Exactly. Yeah, it's so tempting to do that. And in fact, we've looked at a couple of cases where people have done that, right? And unfortunately, there are people who believe this is what scientists do, right? So like, my dad went through like sitting talking at the breakfast table when I was visiting them when they still lived in Michigan. And he was like, well, you know, scientists who are working on climate change, they just make the data say what they want it to. You're gonna find what you want to find. I was like, man, I wish that was true. I'd have a lot more publications, right? Like, it's not actually how data works. And so when something is being found that consistently, right, it's because that consistency actually works. And there can be creativity in data analysis, and that could be both good and bad. And in fact, because there is creativity in data analysis, we in psychology in particular and the other social sciences are able to ask much more complex questions, right? So we have really good tools that are demand that have been devised by other fields, things like t-tests that allow us to compare two groups, right? ANOVAs allow us to compare three groups. A correlation will tell you how things vary together. But oftentimes in psychology and the other social sciences, we want to be asking very complex questions, and the data analysis techniques just did not exist to answer those questions. So psychologists who were mathematically minded sometimes collaborated with mathematicians or sometimes on their own to develop advanced statistical methods that allow us to answer those questions. And so there can be creativity in terms of how we are constructing our data analyses. And sometimes you analyze something and you go, wait a second. This actually probably is showing me something else, right? And so then you check that. And there are ways that you can do that that are not just fishing for what you want to find, right? It could just be something else. So it can be good or it can be bad to be creative in data analysis, right? We don't want to just like test everything under the sun. But at the same time, we want to expand the questions we are able to answer. And again, data analysis itself is theorizing. regardless of whether or not you're intending to do so when you're analyzing your data. So any decisions we make while we're analyzing the data, while we're choosing which analytic techniques to use, imply something about the variables as they exist in the real world, right? So if we're doing an analysis and we just have two groups for gender, right? Male, female, that's what we standardly do within psychology, right? That is implying that anyone who identifies as outside the binary either doesn't exist or at least doesn't exist in our data set, but maybe we just didn't ask that question, right? If we have a Likert scale type questionnaire we're giving, what were you say, are you feeling depressed? Or how depressed are you feeling? Let's do that. And it starts at 1, not at all, goes up to 7, extremely depressed, right? We're saying a couple different things. We're saying people have the ability to judge how depressed they're feeling. This metric is going to capture that. And that's going to give us something meaningful about that, right? And then when we go in to analyze it, we're saying, okay, depression is not a yes, no. Depression is continuous, right? You can be like a little bit depressed or really depressed. And that is implying something about the world, right? That depression exists in grades rather than just you have it or you don't, right? And so these things really do matter in terms of not only how we're analyzing data, but also how we're conceptualizing these variables, these ideas, right? And so how we measure something often influences how we think about it. And so this next video I have to show you all is about p-hacking, which is essentially kind of analyzing your data any way you want to try to get the results. It's what my dad thinks happens, right? I always love when John Oliver covers something because he finds the interesting facts and then does it in an interesting way as well. So he did a little coverage on this a few years ago.
Science, the thing we love and respect so much, we only allow scientists to be portrayed by the likes of Arnold Schwarzenegger, Nicolas Cage, and Al Pacino. That is how much we respect them and the complexity of the world.
Hang on just a sec. There we go. There are like 3 places I can adjust the volume in this. I have to find which one is down low.
They do. Science is constantly producing new studies, as you would know if you've ever watched TV.
A new study shows how sugar might fuel the growth of cancer.
A new study shows late-night snacking could damage the part of your brain that creates and stores memories.
A new study finds pizza is the most addictive food in America.
A new study suggests hugging your dog is bad for your dog.
A new study showing that drinking a glass of red wine is just as good as spending an hour at the gym.
What? That last one? No! That last one doesn't even sound like science. It's more like something your sassy aunt would wear on a t-shirt. Time.com once even ran the headline, "Scientists say smelling farts might prevent cancer." It turns out the study never mentioned either of those things. It just pointed out that certain sulfide compounds are useful pharmacological tools to study mitochondrial dysfunction. And while that Time story was later heavily corrected, the scientists told us that we still get phone calls and emails from strange radio and TV shows wanting us to talk about farts, which is clearly a waste of their time. There are now so many studies being thrown around, they can seem to contradict one another. In just the last few months, we've seen studies about coffee that claim it may reverse the effects of liver damage, help prevent colon cancer, decrease the risk of endometrial cancer, and increase the risk of miscarriage. Scientists are under constant pressure to publish, with tenure and funding on the line. And to get published, it helps to have results that seem new and striking, because scientists know nobody is publishing a study that says nothing up with acai berries. And to get those results, there are all sorts of ways that, consciously or not, you can tweak your study. You could alter how long it lasts, or make your random sample too small to be reliable, or engage in something that scientists call p-hacking. It's very complicated, but it basically means collecting lots of variables and then playing with your data until you find something that counts as statistically significant but is probably meaningless. For example, the website 538 surveyed 54 people and collected over 1,000 variables, and through p-hacking the results, was able to find statistically significant correlations between eating cabbage and having an innie belly button, drinking iced tea and believing Crash didn't deserve to win Best Picture, and eating raw tomatoes and Judaism. And if you think I'm exaggerating about the impact that this misreporting can have on our faith in science, look at an example from some of the people most guilty of it. Because the Today Show, which lives for scientific studies, recently concluded one segment like this.
Like a lot of studies that we love around here, there have been a couple, especially related to women, about the benefits, as I get all serious, on whole milk. Hey, whole milk, but it's true.
Well, there's a lot of research, though, that says actually having whole milk or having whole fat dairy products actually can help you lose weight.
I think the way to live your life is you find the study that sounds best to you, and you go with that.
No! No, 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 no!
Right. And so like that's what happens, right? Is when these studies are so unclear, basically folks just kind of pick and choose, right? And so science as a whole, again, this is why we have the systematic reviews, this is why we have meta-analyses to look at these trends overall. But as you can see, sometimes these are just vastly misinterpreted. There's a couple things that go into that. One is that oftentimes if you publish a study that seems like it has cool data, then the journal has an office of people who are not scientists, but who take it and turn it into a press release, right? And so sometimes translation can get lost there. So maybe we've lost just a little bit of translation, maybe it's a little sensationalized, right? Then the news organizations get a hold of it, right? And maybe they take it yet another step further, like this FARC study, right? And so then as a scientist, you might see your findings just get away from it, right? Which is horrifying, and you don't want to misrepresent yourself. And again, this is why a lot of scientists now are trying to become science communicators via like Twitter or other social media, where they talk about their own studies or other people's studies in a way that is accessible but also accurate. One of the things they mentioned in there that I realized I don't think we've talked about in this class in particular is the tenure system. And so this is not only for scientists, but for anyone who's in an academic setting. So we'll take Wesleyan as an example, although certainly it's very similar to a lot of other places. So when you are hired at a, whether it's a teaching hospital, a research-based hospital, a liberal arts institution like ours, you are typically hired as an assistant professor. And you are hired as, what is the word they use? It's something like contingent faculty. And so the idea is like basically you could in theory get fired at any time. In practice, that doesn't necessarily happen, but it's sort of hanging over your head, right? I need to prove myself so I still have a job. Usually within your first 4 to 6 years, depending on where you're working, you have the opportunity, and in fact, not just the opportunity, you are forced, this is when you do it, to apply for tenure. And so tenure is when you are granted tenure, basically they cannot fire you unless you do something illegal. So I have tenure. If I murdered someone, they could still fire me. But if I say something they don't like, they can't actually fire me. Whereas when I was a contingent faculty member, technically they could, right? And so tenure is in place to try to guarantee academic freedom. So people can study the variables they want to study, so people can speak out and support other people. But the process of getting there is very stressful, and it's like, you've gotta get X number of publications, you've gotta look at your teaching emails, you've gotta look at service to the university and beyond the university. And so this is, I think, where some of the key hacking and other things come in, when people get so anxious about, like, I just gotta get stuff published for tenure, right? Rather than being like, I'm gonna publish the stuff that actually makes sense, right? And I had the liberty of doing that here because we're a liberal arts institution. Yes, research is valued, and all of your folks who teach you will have been published in some way, and for the most part, some of our adjuncts maybe not, but all of your full-time faculty members. But it's not the be-all end-all. Other places where you try to get tenure, they literally call it publish or perish, and it's really scary. So then, when you get tenure, you're typically also promoted to be an associate professor. And then once you feel like you've established yourself well, you can kind of go through a similar process and get promoted to full professor. So that's where I am now. So I feel very secure in my job, which is why I'm so open with you all now. But you know, when you're on that sort of upward contingent line, that there are people who just are so desperate to publish and keep their job, right, that some of this stuff can happen. One of the things that a lot of people are really into now, and is really starting to become the standard for the field, although certainly we're not all the way there yet, is pre-registration. And so the idea with pre-registration is you might even like publish this in a journal, or there are websites where you can just post this yourself, but you basically publish your proposal for the study you're going to do. And so you say, this is my methodology I'm going to use. These are the statistical tests I'm going to run. And then you hold yourself to that because it's out there in the world, right? And so that's part of open science, is to then match that back up with whatever you do end up publishing. And then, as I mentioned previously, open science, you often also now have your data available as a supplementary source, so other people can go in and kind of check you. And a couple reasons for this. Again, it's not, we don't want to assume that anyone is being unethical, right? Or sloppy or things like that. But the hope is that by making more things open access and planned, it will actually help science and help like inspire other folks as well. So you had a article on Perusal where they took one data set and they gave it to a whole bunch of different people and said, let's go ahead and analyze it. And so the goals of the study were basically to see how different is this going to be? How different are the results going to be? What are they actually going to do differently, right? And so they had 61 data analysts, people who are well-versed in how to analyze data, and they gave them all the same data set. And in this particular data set, what the question they were asking is, are the referees in soccer, European football, we would call it instead, right? More likely to give red cards to dark-skinned rather than light-skinned players. And so the data set included data about demographics for the players. It included information about who got red cards, things along those lines. And if you're not familiar with soccer, a red card is a penalty, right? You get a yellow card, that's sort of a lower one. Red card is a big deal. So pretty much every one of these, what was it, 61 data analysts analyze the data differently. And now this doesn't mean every single person used a different type of data analysis. But what they were doing is looking at different covariants. And so covariants are different variables you take into consideration that are not your two main variables, right? Their two main variables here were essentially who gets red cards And are they more likely to be dark skin, light skin, right? But you take other covariants into account. So for example, in my field, when I'm studying body image, a lot of times we include body mass index as a covariant because we know that people who have a higher BMI, because our culture is so driven to low BMIs, often are going to have higher body dissatisfaction. So we sort of take that into account. So you might take into account things like age, race of the ref themselves, level of play, right? How many, you can do analysis to see like how many red cards does this particular ref give, right? And is that influencing it? And so 69% of the data analytic teams did find a statistically significant positive effect. So they said, yeah, refs are giving more red cards to people with darker skin. But there were 9 teams that found no significant relationship. So again, kind of showing if you're adding in a whole bunch of different stuff, right, you might get different responses. Then what I really loved is they had each other, after they'd finished theirs, right, so that it wouldn't bias them for their own analysis, they gave them everybody else's, the other 60 people's analyses, and said, what do you think of how they did this? And then debate and discuss which of those other variables should be included. And so what we found in this particular study is that just using different covariates or slightly different data analytic approaches, we found really different information in the data. Kind of walk over to the board, but it's nearly illegible because of the projector. So I'll read it off of here. So it seemed like, based on the data, based on, again, peer reviewing everybody else's analyses, people were like, yeah, this seems like it could be caused by referee bias. Okay. And this was a 1 to 7. So this is sort of like right around the middle-ish, maybe a little under. Almost directly at the middle here, we have that the positive relationship is likely caused by variables that are not even included in the data set. You know, players' behavior. That's, in theory, what should be causing a red card, right? Is how the player is acting. A lot of them said, yeah, this relationship exists, but from this data set, we can't conclude why it exists. So that was like the highest one that we saw. Others say, you know, there are outliers. So maybe there's one ref who's giving, I don't know, 5 red cards a game. That's probably very unusual. That's probably not quite to that level. Right? But having a couple refs who are doing this to the extreme, right? Or like every time they give a red card, it's to a dark-skinned player, can really affect your data. Others say, you know, there's a positive relationship, but it's contingent on stuff that is in the data set. So they looked at different leagues for soccer, and the refs seem to act very differently within the leagues. Some were saying there's little evidence of a relationship. Some were saying there's no relationship. And some were saying there's a negative relationship. And so I would say the vast majority of people are saying there is a relationship, right? And it's positive. But there are still a decent number of people saying, maybe not, right? And they all were looking at the exact same data set. And so these are the types of analyses that they did. These are all mostly, I'm taking a quick look. Yeah, these are almost entirely, appropriately, things that are based off a correlation framework where you're going to look at how continuous variables are related to each other. Just some are more complicated than others. So like a simple correlation would just be, do the 2 variables relate to each other, right? Whereas something that's looking at like multi-level modeling or mixed effects, right? These are going to be taking into account those covariates to a greater degree. And so what you say is that depending on which one they use, they might have found a stronger result, essentially. All right, so data analysis does matter. Data analysis is very important, right? And so we should be thinking about, as we read journal articles, things like which data analysis are they using, and is that influencing the results that we get, or maybe not. And so now what we're going to do is we're going to start talking about our next lecture topic, which is how to lie with tables and charts. So we've been talking about how to lie with statistics. Even if our statistics themselves are solid, there's a lot that can go wrong when we go to make those a visual representation, right? And if folks had like printed this for yourself or pulled it down before today, I did add some more up-to-date chart examples. But if you go to the Google Drive link to this lecture, they're all in there. So, but I was just like, let's see what's happened in the past 2 years and all kinds of fun stuff. So we're going to start with a little video about how do we spot a misleading graph.
A toothpaste brand claims their product will destroy more plaque than any product ever made. A politician tells you their plan will create the most jobs. We're so used to hearing these kinds of exaggerations in advertising and politics that we might not even bat an eye. But what about when the claim is accompanied by a graph? After all, a graph isn't an opinion. It represents cold, hard numbers, and who can argue with those? Yet, as it turns out, there are plenty of ways graphs can mislead and outright manipulate. Here are some things to look out for. In this 1992 ad, Chevy claimed to make the most reliable trucks in America using this graph. Not only does it show that 98% of all Chevy trucks sold in the last 10 years are still on the road, but it looks like they're twice as dependable as Toyota trucks. That is, until you take a closer look at the numbers on the left and see that the figure for Toyota is about 96.5%. The scale only goes between 95 and 100%. If it went from 0 to 100, it would look like this. This is one of the most common ways graphs misrepresent data, by distorting the scale. Zooming in on a small portion of the y-axis exaggerates a barely detectable difference between the things being compared. And it's especially misleading with bar graphs, since we assume the difference in the size of the bars is proportional to the values. But the scale can also be distorted along the x-axis, usually in line graphs showing something changing over time. This chart showing the rise in American unemployment from 2008 to 2010 manipulates the x-axis in two ways. First of all, the scale is inconsistent, compressing the 15th-month span after March 2009 to look shorter than the preceding 6 months. Using more consistent data points gives a different picture, with job losses tapering off by the end of 2009. And if you wonder why they were increasing in the first place, the timeline starts immediately after the U.S.'s biggest financial collapse since the Great Depression. These techniques are known as cherry picking. A time range can be carefully chosen to exclude the impact of a major event right outside it. And picking specific data points can hide important changes in between. Even when there's nothing wrong with the graph itself, leaving out relevant data can give a misleading impression. This chart of how many people watch the Super Bowl.
So just to like take a little pause here to talk about this. So to give it some context, why that graph not including the recession is really important is because I believe that was a Fox News graph, and they were trying to imply that Obama's presidency was what was causing the job loss. Whereas Obama sort of inherited this horrible economic crisis, right? Like I remember sitting in an airport in December 2008. So like Obama had been elected, but not even inaugurated yet. And it was just everything was going to shit, right? Like everything looked horrible on the TV. And then that's when like the auto industry started crashing and things along those lines. And then like, if you just sort of cherry pick, you can make it look like, oh, well, this is the fault of who's in charge now rather than what happened before that.
Can give a misleading impression. This chart of how many people watch the Super Bowl each year makes it look like the event's popularity is exploding. But it's not accounting for population growth. The ratings have actually held steady because while the number of football fans has increased, their share of overall viewership has not. Finally, a graph can't tell you much if you don't know the full significance of what's being presented. Both of the following graphs use the same ocean temperature data from the National Centers for Environmental Information. So why do they seem to give opposite impressions? The first graph plots the average annual ocean temperature from 1880 to 2016, making the change look insignificant. But in fact, a rise of even half a degree Celsius can cause massive ecological disruption. This is why the second graph, which shows the average temperature variation each year, is far more significant. When they're used well, graphs can help us intuitively grasp complex data. But as visual software has enabled more usage of graphs throughout all media, it's also made them easier to use in a careless or dishonest way. So the next time you see a graph, don't be swayed by the lines and curves. Look at the labels, the numbers, the scale, and the context, and ask what story the picture is trying to tell.
So that becomes really important, right? Is like, what is the context outside of this? And like the vast majority of time, you don't want to squeeze in, right? But for that ocean temperature data, because we know those small changes can make such a difference environmentally, squeezing in on them becomes really important to look at those differences. This is my favorite one I've ever seen. I found this morning. Who can tell me the major bubble of this one? Like right at the top of that house. Yeah.
I'm gonna say at least like 37% are not the suicide.
Exactly, right? So like 2 people got the same percent of votes, it looks like, but 137 is better than the other 37. And there's probably that one did get like a percentage point higher or whatever, like, 37.5. But in that case, say that, right? Don't label it both as 37. It's problematic. This is from a paper in the UK where they have national exams called A levels. Are they becoming harder to pass? I don't know if they just took a standard pie chart and just plopped their numbers on it, because they certainly don't actually represent the percentages. Right? It could be like 50 and 49 and then like undecided, right, for 1%. And again, so sometimes these are not malicious, right? They're not, sometimes they are. Sometimes they're purposely trying to sway you one way or the other. But sometimes they're just really bad use of data visualization, right? Where someone's been quick or careless, and just sort of thrown something together and then it gets published, right? This was another good one I found this morning. So this one is saying the KFC crispy chicken twister, which I don't even know what that is. It must not have lasted very long, right? And they were trying to say, like, it's better than some of these things, but like worse than pizza. But again, we have a very small calorie range here, right? So they're saying, well, this is only 650. Look how much more these other things are, but it's not even 100 calories more, right? And then if you think about those little like 100-calorie packed snacks you get, it's really not that much more proportional. And it also makes it look like pizza has very few calories, when in fact the snack is starting at 590, right? And so problematic, misleading, just sort of hard to wrap your head around after a certain point, right? we've looked at this one before, right? So just the idea of like not taking into account what percentages are, right? This is more than 100% by a lot. And they're probably different questions, right? But then don't put them on the same graph implying they're all the answers to the same question. Right? That makes it confusing. That makes it difficult. Because what this means is that there are boomers who describe themselves as people savvy and willing to learn and leaders and creative, right? But this implies that it was like a one or the other. Another, just what are we doing? Pie charts, right? And again, with the sections not even really matching up. This was for the 2012 campaign. It took me a minute to remember there. And so again, similar to the one we just talked about, they asked Republicans, who would you be willing to back if they were the nominative candidate, right? And so it looks like basically 60% of people said, I would back any of them, right? I'm gonna vote Republican. But again, if they would have asked, like, will you back Romney? And 60% of people said yes, right? Will you back Mike Huckabee? 3% of people said yes. Will you back Sarah Palin? 70% of people said yes. But again, by putting them all on the same figure, it seems to imply that these were all the same question. And that's not what was happening here at all. This is something that until I taught this class a couple of years ago for the first time, basically the class was brand new, I had never seen before, but these like donut charts are something that is kind of trendy. People think that they make it easier to understand data. But in fact, if I look at this, I just get really confused, right? Until you take a minute to like process it. So this is trying to show what federal subsidies go for, right? And here they are acknowledging that these are different questions, right? They are saying, you know, like the fossil fuel subsidy is different than the renewable energy subsidy and things along those lines. But because they've embedded so many other things within one, it's really hard to sort of parse out what it's actually trying to say, right? So essentially, I think what it's saying is fossil fuels are actually this whole half over here. Whole half sounds weird, but you know what I mean. And then there's other little pieces in here, right? But like just glancing at it initially, it's like, oh, what? What are you saying? And then they've got these little pieces in here, 5 billion, 11.8 billion, they don't even tell you what they are, right? So this graph, this chart isn't really like telling you that much meaningful information, even though they're trying to make it look like they are, right? And then they're also trying to make it look like the renewable energy is getting as much as the fossil fuels, when in fact the fossil fuels are 72.5 billion and the renewable energy is only 29 billion, right? So even just that is off. I think, I mean, again, this is really hard to read, so I think that's what it's saying. This is Major League Soccer player salaries. And this is like the union for them released them. And so this is just every Major League Soccer player's salary kind of put onto the same metric. I think they're also trying to show the budget for the team as a whole. So obviously LA has a much larger budget, right? But it's sort of like there's no x-axis, so we don't actually know how much those are, right? This guy gets $5 or this guy gets $5 million. I mean, probably that one, right? But we don't know. Right, I think there's some indication over here. It's like maximum of 36,500, 750. There's still only an estimate of cap, yeah, it's just sort of like, what is this actually telling us, right? The idea behind creating tables and figures is to give us more information, not to leave us befuddled, right? And this just sort of leaves us befuddled. Again, this is something about where your food comes from. I think part of the problem that happens in making tables and charts really hard to read is when people try to be clever, right? So this is an example of this. They're like, "Ooh, look, we used food because we're talking about food." And again, when you look at it, you're sort of like, what? And so you have to read this text over here, which is not the biggest, to understand that, like, what we're looking at is the percentage of these foods that are imported into the US, right? And so, okay, we've got like 61% of honey, 20% of fresh vegetables, and for whatever reason, melons are with the vegetables. I don't know why. And then you got fruits and nuts, but then you have another fruit over here. So what's happening there, right? This definitely looks like way more than 52% of the lamb to me. Right? It looks more like the 88% for the seafood there. And then I think these are showing which countries these come from, right? But then it's like you're using percentages and you're not really explaining that these are percentages of that percentage, right? And so again, it just gets more confusing instead of less confusing. And then this one, I get what they were doing. They were trying to show sort of the percentage of people who are of different ethnicities, right? Within the US. And again, trying to be clever by using the US as our metric, right? But in so doing, and just sort of plopping it on there and making the US essentially a box to hold the stuff, right? You could look at this and it implies that, like, anyone who's of other race lives at the very top of the name, right? And that the South and the Southwest are all white. And in fact, we know that that's some of the most diverse areas of the country, right? And so again, people trying to be clever, unfortunately, leads to a lot of this confusion. Just like, take a sec. And tell me what's wrong with this one. Yeah, the bars are just not proportional at all, right? Yeah, the 5% is almost as much as the 91%. You know, the 1% is more than half of the 3%, right? And so these would actually be way down here if we were being proportional, right? Most of the people, I think it's like a college paper or a high school paper. So again, I like to give some grace, but also somebody copy edit this, who knows what to do, right? And professional papers have done this whole course. But like workforce would be down here, right? You're in the military, if you're really small, taking your off should be pretty small as well. Again, just, I don't know if these people just got confused, didn't know how to bar graph. But they certainly bar graphed a bar graph, right? So it's just like the 13% is bigger than these other ones. Did the data get mixed up? I don't know, right? And again, this was on a local news station, a professional news station run by people who should know better, right? And yet that happens. All right, we'll go ahead and end there for today. We'll keep talking about this on Wednesday. And either Wednesday or Friday, we have an activity we're going to do related to making figures as well.